but this is actually the equation that's used for the runoff volume portion, and it's a really easy calculation to do. Any of us could do it. It's based on something called the curve number. You guys are familiar with that, but the curve number is a value of anywhere up to 100. 100 would be the highest, where all of the rainfall becomes runoff. As that curve number goes down, that means that there's less runoff volume created by that land area. So if you have a forested land cover, you're going to have a much lower curve number than if you have an impervious land cover. A parameter, the S value here, is based on that curve number. And then using that in the precipitation, you can come up with a calculation of how much runoff volume is being created by a site. So you could do that on a calculator, Excel spreadsheet very easily. You can come up with the runoff volume for any given site if you know the precipitation, the land cover, and the soil types. There's also an initial abstraction number, which is 0.2 times that S value. That's the amount that gets soaked up by the soil for a given curve number. So you can see as that S value goes up, so the curve number is going down. As the S value goes up, you're going to have a higher S number and higher initial abstraction. So wooded site's going to soak up a lot of that water. Meadow site's going to soak up a lot. Impervious, there's almost no initial abstraction. All of that water is becoming runoff. So we talked about volume there. Also going to be talking about peak flows here. And again, NRCS methodology is used for calculating peak flows is recommended. And this is a little more complicated than just a simple formula. This is using a TR20 methodology. It's a more complex methodology that uses rainfall distributions. In New Jersey, there's two rainfall distributions that are used depending on where you are in New Jersey. It's either the NOAA Region C or D rainfall distribution. And the flows are calculated using a unit hydrograph, which is based on a rainfall distribution, kind of a typical rainfall distribution for that area. So you're using that unit hydrograph, you're using that curve number that we talked about within the watershed, and then a time of concentration, which I'll talk about in just a minute. So in New Jersey, when you're doing work on water quality focused designs, you're looking at the 1.25-inch storm event, which is a 2-hour storm. So you could think of this as like a thunderstorm that comes around at 2 hours, kind of a quick peak. It's a lower volume than some of these larger water quantity storms, but it's based on a 2-hour distribution of rainfall and a total rainfall amount of 1.25 inches. For water quantity design, we're looking at the 2, 10, and 100-year storm events, and those are calculated using a 24-hour distribution. So it's a longer period of rainfall and higher depths of rainfall for those storms. And one thing to mention here, coming down the road shortly in 2023, there's proposed inland flood protection rules that address stormwater rainfall depths for these distributions. And these new rainfalls will require use of future projected precipitation when calculating for flood elevations and for stormwater design of stormwater management BMPs. So that we're looking at designing for that resiliency and climate change, where the climate science is showing that the rainfall depths are going to increase over the future. And finally, I mentioned time of concentration. Some folks don't fully understand this concept, but the time of concentration is defined as the time it takes for runoff to travel to a point of interest from the hydraulically most distant point. So it's not necessarily the farthest point away, it's the point that takes the longest time for a drop of water to move from the most upstream part down to the outlet of a watershed. And I think it's not quite understood how important that is, especially for peak flows. So you could have different times of concentrations. As that time of concentration is longer, the peak flow is going to go down quite a bit for that same runoff volume. And one way to think about that, we're in kind of a smaller size room here. You could think of all of us as the runoff volume in this room, right? Pretty small room. If I said, everyone, there's a fire drill, go out the door, we're all going to run out the door, right? We're probably going to go through there pretty quick, all of us at once. If this was a huge auditorium, same runoff volume, but some of us are very far away, it's going to be a trickle out the door, right? If someone from here leaves and someone farther away. So for that same runoff volume, as the time of concentration increases, That's a dramatic decrease in the peak flows that are occurring at that watershed. So with that, I'm going to talk a little bit about the what happens when we start developing watersheds from undeveloped forested area, for example, to an urbanized area. So what are those impacts of development? I call this the urban hydrologic cycle. You can see as rainfall occurs on a land area that has a lot of impervious coverage, you're going to have a lot less infiltration of water moving into the ground. It's going to hit those paved areas and run right off. Obviously, you're going to have a big increase in the runoff volume and the peak flows that are occurring in our streams. Increased, more frequent flooding. But we're also going to have reduced groundwater recharge because you have less going into the ground, less getting into our groundwater aquifers. And those groundwater aquifers is what's feeding our streams during dry periods of time. So you have this paradox now of when it rains, we have these huge flashes of flow going down our streams. But during dry weather, you have a lot lower flow, which is not good for water quality. You also have increased pollutant loading. So we're talking a lot about the TMDLs. What is that? Pounds of pollutants that are getting to the surface waters. And so since we have a lot more volume of water and we have that water carrying a lot more pollutants from those land uses, those pollutant loadings are going up dramatically. And here you can see what a typical change from pre-development to post-development if you're adding impervious coverage. So that area under the curves is going up dramatically for post-development. That's showing you that the volume is increasing. The peak flow has gone up dramatically. And you can also see that that peak has shifted sooner. And that's because that time of concentration has gone down. So you have that shifted peak happening earlier, the increased volume, and the increased peak flow. All which is wreaking havoc on our streams and surface waters downstream. I'm going to show two different, this is actual data from back in 2014. One is up near Wanacue, New Jersey, which is a relatively undeveloped watershed. So more wooded areas, largely wooded areas, pervious areas, very low impervious coverage. And you can see there's rainfall events that are occurring. You can see that hydrograph kind of coming up and down. But I want you to take a look at here is the scale of about 5 to 400 at the biggest peak happening in the beginning of this period, which is April 2014 to August 2014. This is an 18 square mile watershed. And then let's compare this here with the Elizabeth River hydrograph, which is a very urbanized watershed. So it's actually a smaller watershed, but now you see the peaks at 4,000, right? So it's a dramatic difference. And you know, this area was once an undeveloped area. The streams weren't meant to carry this high peak flows, this huge quantity of volume, right? So everything we're doing here is trying to get back to mimic that natural hydrology where we don't have these very flashy streams where we have huge peak flows, flooding, back to mimic the natural conditions where we have more of a base flow condition with smaller peaks for storms. So back in 2004, FEMA looked at all the potential hazards, natural hazards that could occur in New Jersey, and they determined that flooding is New Jersey's #1 natural hazard that they would see in the coming decades. And they were certainly correct. Since 2004, which is when I graduated college, there's been numerous storms, a 100-year storm after a 100-year storm, 500-year storm, where there's been dramatic flooding events from Delaware floods in 2004 to 2006. Irene came through in 2011, and then Ida most recently in 2021. And not including, you know, every other year it seems like there's a storm like this that comes through causing significant damage. We've also heard a bit about TMDLs and water quality impairments. This is a list of some of the typical impairments that exist in New Jersey streams. I was actually shocked at that mapping that shows the whole state basically, right, is either an impaired waterway or TMDL area. But things like pathogens, toxics, metals, We heard about nutrients, phosphorus and nitrogen, dissolved oxygen and pH impairments, temperature impairments, and TSS impairments. So this all exists in New Jersey. It's all things that we need to look at looking at these watershed improvement plans. Some photographs here of sites that we've looked at in the past. There's some from the Raritan River where there was a nutrient TMDL, an ag station there, and eutrophication and algae growth in a lake. On the top right is in Monmouth County, where they have glauconitic soils that are highly erodible, and so these streams weren't designed to to carry that much flow. And you could see the extensive erosion that occurred as a result of that, carrying with it TSS and pollutants downstream. And then on the bottom left is a site in the Passaic River where we have toxic issues, metals, trash, DSS. And so all these require implementing stormwater BMPs to address these water quality impairments. So like I mentioned, I will be talking about the New Jersey Stormwater Management Regulations. For those of you that are not familiar with them, these are designed or in place to address new development and redevelopment projects in New Jersey. They get triggered with over an acre of disturbance or over a quarter acre of impervious surfaces. And there are 4 components to these regulations. The first is water quantity. The second is groundwater recharge. Third is water quality. And the fourth, which used to be non-structural approaches, is now green infrastructure. And so I'll go through each of those real quick. For water quantity regulations, there's 2 options to meet this standard. The first is to reduce peak flows from pre-development to post-development conditions, where you need to meet 50%, 75%, and 80% of post-development peak flows in the 2, 10, and 100-year events. So you can reduce that peak flow in order to meet the criteria. The second option is to reduce flow below pre-development conditions at all times during the hydrograph. So this is basically your approach is trying to match that pre-development hydrograph, mimic the existing hydrology, and this requires that you have no increase in runoff volume. Just to give you how this would look in a hydrograph, the first would be peak flow reductions here. And the second would be the light blue line for the second method, which would be the matching hydrograph. So the first method may not reduce the volume, right? You might have more volume in the post-development condition than the pre-development condition, but you're reducing that peak flow per the criteria. Versus the second, you're reducing both the peak flow and the runoff volume. For groundwater recharge, in order to meet that criteria, again, there's 2 options in order to show compliance with that. The first is using a spreadsheet model that NJDEP developed. It's called the GSR32 spreadsheet model, which looks at your pre-development conditions and post-development conditions over an entire annual period and calculates a amount of annual recharge that's occurring on the site. So you look at that from pre-development conditions to post-development conditions, and you see if there's any deficit that was created as part of your project. If there is a deficit within that spreadsheet, you can plug in different types of BMPs to show that you are mitigating and offsetting that deficit with, like, for example, an infiltration basin or infiltration trench. The second option is you can demonstrate that there's no increase in runoff volume during the 2-year storm event. So that would be using more of a modeling hydrology approach to demonstrate that there's no increase in runoff volume. Designers can use infiltration from BMPs to show compliance with this requirement. And there are some cases where this is not required. There's exemptions for it, and one is in urban redevelopment areas. For water quality, you must meet an 80% TSS load reduction for all new impervious surfaces. Redevelopment is addressed here to some extent, where you have to meet 50% for TSS load reduction from a redevelopment impervious surface. And someone asked in a previous talk what the definition is there for redevelopment. It's basically just the replacement of an existing impervious surface with an equal area of proposed impervious surface. So for those areas, there's a reduced amount of treatment that's required to 50%. We did hear earlier from DEP that they are looking at raising that to 80%, so that 80% is required for both new impervious and redevelopment as part of the PACT rules. So just showing some of the typical TSS removal rates, some of the more efficient systems out there are bioretention systems, constructed wetlands, infiltration systems, impervious paving systems. All of these have either a very good treatment aspect to it, or they have a good component of infiltrating and reducing runoff volume, because both of those methodologies are using volume reduction and treatment will provide a high TSS removal rate. There's also a section in the BMP manual on nutrient, phosphorus and nitrogen removal rates. There's not a numerical target. It just says to reduce to the maximum extent practical. And this is rarely talked about, but it is in the BMP manual. And this shows some of the phosphorus removal rates and nitrogen removal rates for the different BMPs. And again, it's those same systems that have high treatment efficiencies and have a component of infiltration that have higher removal rates for these parameters. So that brings us to green infrastructure. There is now a green infrastructure component of the regs in which they say that those three categories, the quantity, the quality, and the groundwater recharge, have to be met using green infrastructure. And so the definition, this is the NJDEP's definition, so this is the one that counts, is methods of stormwater management that manage stormwater close to its source and reduces stormwater volume, flow, or characteristics by allowing stormwater to infiltrate, treated by vegetation or by soils, or be stored for reuse. So all of these green infrastructure BMPs meet that definition. And some examples are pervious paving, rain gardens, vegetated swales, cisterns, which have that reuse component, green roofs, and vegetated filter strips. And so I'll go through some examples of those in a little bit. And just to give a complete list here, this is a table taken from the latest version of the stormwater management rules. These are the BMPs that are satisfying the definition of green infrastructure in NJDEP's view. So same kind of ones that I was mentioning before. A lot of these have small scale next to them. So you can see small scale bioretention, small scale infiltration. And so those have a maximum contributory area, which I'll mention what those are in a bit, but they limit the size of these because they want you to design them so they're close to the source. So they don't want some large centralized basin where you're sending all of the water from a very large site. A, it doesn't work quite as well. B, you're then focusing all of your infiltration in one spot on the site, which tends to not be as effective. Also on here is manufactured treatment devices, but only green infrastructure versions of those. And again, I'll talk about manufactured treatment devices a little bit in a future slide. But those are the types of green infrastructure like tree pits, bioretention treatment devices that have that soil infiltration component to them, as opposed to, let's say, a hydrodynamic separator, which is more of a traditional non-green infrastructure device. There are also a list of green infrastructure BMPs that are these larger systems, like I was mentioning, that don't meet the close to its source definition, but DEP does allow to meet quantity, because when you have a lot of small systems on a site, it gets hard to manage that really big 100-year storm event. So there's often a need to design a larger system in order to manage those peak flows from a site. So if needed, these types of BMPs, like a larger bioretention basin, a larger infiltration basin, can be used, but can only meet that quantity criteria. You'd have to have the smaller type systems for the quality and groundwater recharge storms. And those maximum contributory drainage areas, it's 2.5 acres for most of these different types of BMPs, including bioretention systems, infiltration basins, sand filters, and manufactured treatment devices. Importantly, contributory drainage area means the area that actually drains to the stormwater management and does not include the area of the stormwater management measure itself. So you wouldn't include the actual footprint of a bioretention basin in the calculation of what that contributory drainage area is. Okay, so I'm going to move here just to recap real quick. I'm not sure if you were in the earlier presentations, but this would be a little bit of a repeat here. What the MS4, the latest MS4 permit, what the watershed improvement plans are all about. So these are the goals that are listed in the adopted Tier A MS4 permits. And as we learned earlier, there are no more Tier B. So all communities in New Jersey, all municipalities are now Tier A communities. And they have a requirement now to develop a watershed improvement plan with the following goals. So the first two have to do with water quality and focusing on reducing contribution of pollutant parameters for either TMDL watersheds or waterways that have impairments as per NJDEP's integrated report. The third one is to reduce and/or eliminate stormwater flooding in the municipality. So it has the water quality and the water quantity components to it, which is why green infrastructure is a great option to look at in order to chip away at those goals. And also, as discussed earlier in some of the talks, the MS4 permit improvement plans have 3 different phases, and they're designed to build on each other, right? So the first one is due after 3 years, the next one after 4, after 5. And in my work that I've done in my career on watershed restoration, we've used a very similar approach, right? You can't go right to putting projects in the ground if you don't know where your infrastructure is, if you haven't assessed where the high pollutant loading areas are. So we need to consider all of that. Jim, I think you mentioned earlier in one of your questions, you could put a bioretention basin on a site that doesn't have a lot of load, right? And you can say, oh, great, I'm getting 80, 90% removal. But if you're starting with nothing, you haven't removed anything, right? So you need to find out where those sites are that are creating TSS, where those sites are that are creating whatever you're impaired with, so that you can target those areas specifically to get the most bang for your buck. So those 3 phases are the watershed inventory report. That's the summary and mapping of the various stormwater infrastructure, the drainage areas, different interconnections, outfalls, receiving waters, looking at where the TMDLs and impaired water bodies are in your municipality. Then a focus on looking at where those overburdened communities are and impervious areas are within your watersheds. The next is a watershed assessment report. You're taking it now a step further to assess what potential projects there are, where those targeted areas should be within your watersheds, estimating what kind of water quality load reductions you'll get from these different projects. There's this feedback and public information sessions that are part of this process, which is really important. And then assessing different funding needs. You know, maybe you're looking at New Jersey Water Bank as a good option. Looking at stormwater utilities, 319H grants, FEMA grants, all the different options that there could be to fund these different projects. And the hope is that as we develop these improvement plans, more and more funding options will come up. And then finally, an estimate of what the implementation schedule would be for the different projects getting these in the ground to create those improvements. And then the third step, the third phase is these final watershed improvement plan report that puts this all together, finalizes the proposed locations where you'll be doing water quality improvement projects, a summary of that public comment period, regulatory requirements and coordination that's needed. And you'd think that, you know, if you're doing something that's part of a watershed improvement plan, you might not need, you know, as much permits, but we found doing watershed work in the past that those same rules still apply. Those stormwater management rules often still apply. You still need to get your wetlands permits. You still need to get all of that permitting, and that all takes time. So that coordination is really important, especially on the implementation side. Then coming up with the proposed implementation schedule, public information sessions, identifying any jurisdictional issues, final cost and funding opportunities, and then how you're going to prioritize work within overburdened communities within the watershed. And just wanted to create here a link, a couple links that would be useful in thinking about as we start looking at watershed improvement plans and how we're going to start working on them. There's the final MS4 permit. There's a link to that. There's the final MS4 permit deliverables timeline. That's a really good one to know, when everything's going to be needing to be adopted, implemented, when you need to get those reports together. I also have a couple links here from EPA. The first is the handbook for developing watershed plans to restore and protect our waters. It's got a ton of good guidance from the federal level on doing this type of work. There's also a pollutant load estimate tool, PLET. That's used a lot in 319H work, and I think it has a lot of value here as well. DEP hasn't given a lot of guidance yet on how they want pollutants to be, load reductions to be estimated, but this would be a good starting place. You can plug in your watershed. It's got all of the assumed loading values for different land uses that you can pull up. This used to be called Step L, which is another type of loading estimate tool that was used for watershed planning. They've improved it a bunch. It's now a web-based tool. It used to just be an Excel spreadsheet. It's now a web-based tool. So it's something you can just go in, you can create an account, and you can start playing around with it for your watershed. And finally, I linked here to the New Jersey Green Infrastructure Municipal Toolkit. This is a New Jersey Future initiative that was put together. It's focused on municipalities as opposed to developers. They do have a developer toolkit as well. But this is a great resource that looks at design examples of different BMPs, funding opportunities, everything that municipalities can go to for incorporating green infrastructure in their communities. All right, so we're going to switch gears here. I'm going to start actually talking about the different types of BMPs and how we go about designing stormwater management facilities and green infrastructure. And I like to look at the planning concept here as it's kind of low-hanging fruit to things that are more complex, right, from the top to the bottom here. The first being non-structural strategies, low-impact development. These are more planning tools, things you should think about before you go right to we need to build a huge basin over here. There's might be things that you can do, like reducing impervious coverage, using vegetated conveyance instead of pipe systems that send that water straight to the streams. You can disconnect impervious surfaces, right? You might have downspouts from a whole neighborhood that go right into a pipe system. Maybe you just disconnect those downspouts, let it go over impervious areas. You can have a big benefit for not much cost. This is the same process, by the way, that I go through if we're doing a development site. A lot of times we get brought in to do the stormwater management for a development, for example, and we'll get the plan. It's already, all the houses have been laid out already, and they've got one lot that's where your detention basin's going, right? It's all been done already. And that's kind of a hard spot to design stormwater management from. It's much better to start thinking about all of these things when you're starting to lay out where your improvements are going to go, where you can start incorporating vegetated conveyance. You can just disconnect impervious surfaces. You can try to preserve different areas of the site that have a high value from a stormwater management perspective. The next component there is green infrastructure, and that's that types of stormwater management that's close to the source, like rain gardens, pervious pavement, bioretention swales, and I'm going to focus there for my discussion moving forward. And then beyond that are more of the structural BMPs that are the larger, more conventional type of systems, like larger extended detention basins, larger wet ponds, constructed wetlands. And then I mentioned this before, but volume matters. This chart is a little bit hard to understand, but I'll kind of walk you through it. This is showing how quantity and quality are related to each other. So on the y-axis here is the effluent pollutant loading. So this is the concentration or the amount of pollutants that are leaving a site. And the bottom, the x-axis, is the percent reduction in volume that you're achieving from the runoff leaving a site. And this is all based on a starting point of, before you put any BMPs in, that you have 1,000 pounds of pollutant per day. So you can see here that as that percent reduction in volume is going up, you're reducing that effluent pollutant loading without doing anything for pollutant removal efficiency. So that yellow line represents 0. If you had a BMP that had no pollutant removal efficiency, but you were getting a lot of volume reduction, you would be drawing down that effluent pollutant loading because the loading is based on that volume times the concentration. So effluent polluting loads are equally dependent on both the effluent concentration and that volume reduction. So any BMPs that we can set up to retain that water, infiltrate it, is going to have kind of double benefit of providing treatment and reducing the volume as far as the effluent loading downstream. So I'm going to go through some of these different concepts here. Disconnection is one of the easiest things we can do, right? So what is disconnection? It's directing runoff from impervious areas to a vegetated area that allows infiltration, filtration, and increased time of concentration. So simply by doing that, we can have a huge benefit of the quantity and quality of stormwater runoff downstream. And when we're talking about watershed improvement plans, where we're trying to fix existing issues, this is one of those kind of low-hanging fruits where can we disconnect stormwater runoff from impervious surfaces? Maybe we direct it to a rain garden. Maybe it's just over a vegetated filter strip. On the bottom right there is from the Stormwater BMP manual, just a concept profile view of a paved area going into a stone cutoff trench and then being dispersed over a vegetated area. Very simple thing to do that has a big benefit downstream. There's actual calculations that can be done for measuring that benefit of disconnection. The BMP manual has 2 options that allow you to connect what that reduction in volume would be. The first is kind of a little more complicated based on TR55. It's an unconnected calculation of curve number where you get a reduced curve number based on that percentage of impervious, unconnected impervious to total impervious areas. So as that unconnected impervious component goes up, that curve number drops. There's also a 2-step technique that is allowed by NJDEP. And the way you can think about that is if you have a paved area that you're putting over a grass area, you can treat that runoff from the paved area as precipitation, extra precipitation on the pervious area. So the reason it's called a 2-step technique is you have to calculate step 1 what that volume is that's being generated by the paved area, and then you have to artificially increase your precipitation in the second step to calculate what the total runoff would be downstream. So some pictures and examples of vegetated filters and vegetated swales. These are great options for green infrastructure. The top left is a vegetated swale that was done adjacent to a parking lot. It was just a slotted curb in that case that just allowed water to go through the slotted curb into the swale. And we utilized check dams, in that case it was gabions check dams, to help slow down runoff moving through that swale. So it gives the water an extra chance to retain, infiltrate into the soils to reduce how much is going downstream. On the bottom right is just an example of a detail for a check dam using gabions in order to slow down that runoff. And these are just some more examples of check dams that we've used over the years in different applications. Again, in these vegetated conveyance, really give the water a chance to retain in those BMPs, infiltrate, and reduce flows and volumes downstream. I then wanted to switch gears here to bioretention systems and rain gardens. These systems are one of the more effective and versatile options that we have in our toolbox in order to provide high treatment efficiencies and allow for that infiltration component. And on this slide, I have several pictures of examples of bioretention systems going in at different phases of construction. But the components here are shown in the top right diagram where you have a soil planting bed that's put in. This is an engineered mix that's a very sandy mix that allows water to move through it quickly. It's a very permeable planting bed, but it has organics mixed into it so that it supports vegetation and vegetation growth. And you can see there's two options shown there. On the left is an option with an underdrain. So in that option, you have that soil planting bed at the top, and then a 6-inch thick sand layer. And that's just a bridging layer to make sure that that soil planting media doesn't get down into the underdrain. And then below that's the underdrain layer, which is a crushed stone, open graded layer where water can collect beneath the rain garden. On the right is a system that does not have an underdrain, and it's just that soil planting media at the surface, and then the subsoil uncompacted below it. And the difference here is on the right is where you have good subsoils where that can have high infiltration rates, the existing soils, that it can take that water that's being generated and trying to go into the ground and can drain that system relatively easy. Where you'd use an underdrain is if you have poor subsoils, let's say you had clay that can't accept a lot of water, it can't drain it quick enough. So you end up, if you don't have an underdrain, you'd end up with a pond that could become mosquito breeding habitat. It would just sit there. And so you need that underdrain to help drain that system after a rainfall event. On the bottom left here, I wanted to mention that's a project that I did in Lawrence Township. That was a rain garden that was done when I was on the Environmental Commission in Lawrence Township. That was a total volunteer effort. The DPW dug it out. They had a load of sand that we'd use to amend the soil. And the only expense we had for that whole project was just the plugs for the vegetation, which was all a volunteer effort. So this can be done very inexpensively on a municipal level if you have the will from the municipal community to get it done and you have volunteers. A big thing that I found with that project, for example, is having a group in the community that's willing to take it on. So putting it in is great. You want to be able to maintain it moving forward. So there needs to be some ownership from the community in order to see it succeed throughout the life of the BMP. So the bioretention system has a lot of water quality benefits. So the TSS removal rate is 80 to 90%, a very high efficiency, a very high efficiency for removing total phosphorus, and then 30% for nitrogen as well. And in order to receive the credit for this, you have to show that that water moves through that bioretention media and is filtered through that bioretention media. So if the water is overflowing through a spillway in a water quality storm, not all of that water is getting treated. And there's a lot of ways in which a bioretention system provides that water quality benefits. There's settling and filtration that happens in that surface pond before it even makes its way down through the media. Then as it's moving through the media, there's different types of sorption processes that are occurring. It's removing sediment, but it's also providing sorption for nutrients, for example. There's different transformation processes with bioremediation, phytoremediation. Those plants that are in the rain gardens, for example, are taking up the water in the systems and providing nutrient and pollutant removal that way. And then finally, as I mentioned before, that volume reduction is a very important part of pollutant loading benefits from these systems. So bioretention vegetation, it's based on a simulated terrestrial forested community to get the highest treatment efficiency. And this is a mix of grasses, shrubs, different types of herbaceous species, trees can all be planted in these systems. There's an example on the bottom right here of a rain garden that we worked on at a school. We want to be using native vegetation, diverse species, and we want plants that are able to be inundated with water, flood adaptable, but also be able to handle dry conditions, because these systems, when they're functioning and the water's coming in, it's very wet conditions, but then it can also be very dry conditions between storms. All right, so I'll shift gears here to pervious paving systems. This is a great option, especially for different retrofit options where you have maybe a municipal parking lot where you can convert different areas into pervious surfaces. There's there's different types of surfaces that could be used. On the top left is a porous asphalt site. In that picture, the stalls where the cars are parked is actually porous asphalt, where the driving lanes is standard asphalt. I went out in a rainfall event. You could see the water sheet flowing off that traditional pavement and then just going right into the ground over the pervious asphalt sections. There's different types of paving systems where open aggregates used between the pavers in order to let water move through. And the bottom right is a turf paver system where those blocks have soil that's in between it where grass can actually grow. A lot of times we'll use that for different types of applications where there's not frequent road traffic. So the bottom right picture there is for a pump station where the municipality needs to access the pump station for infrequent maintenance. So they might use it, once a quarter, but they'll need to get a vac truck through to suck out stuff from the pump station. So that provides a way for them to access it safely, but also have that pervious component to it. And the top right shows a typical cross-section of a pervious pavement system where you have a surface course of that pervious asphalt material. There is that the choker course that provides a bridging gap to the open graded stone below it. And then there's that open storage where you can store that runoff, right? If that underlying soil can't infiltrate that very quickly, you have a storage volume where that water can sit for a period of time after a storm event and infiltrate into the ground. And this just shows some different typical details that we've used. On the top is a porous asphalt detail where you have that surface wearing course and a base course, and then that open graded storage below. You can design these with an underdrain if you have poor soils, just like you do by retention. But we found that even with relatively low infiltration rates, if you don't have a ton of water coming into this off of the pervious pavement sections, you don't need a ton of storage, even at a low infiltration rate, for that to get into the ground, because there's not that much depth that's needed from a typical rainfall event. And then on the bottom section is a precast concrete turf paver, like the project I showed on the previous slide of the access way. Dry wells and cisterns. This also would include like an infiltration trench. These are all underground systems that can manage volume, right, from relatively clean runoff. You don't want to put in paved areas that have a ton of sediment directly underground, because you're going to end up clogging the system really easily. But let's say you had a rooftop that you wanted to disconnect. Going underground would be a really good option, right? Because you're not going to clog it up very easily. You can manage that water. You can recharge it into the ground very effectively. So these systems that's kind of their place, is for taking relatively clean runoff and managing that volume to get it into the ground. Cisterns are also an option for managing, again, volume for rooftops, for example. You can think of rain barrels. On the bottom left is a much larger cistern. That's from a Rutgers project that they did in Clark at a DPW site. That project involved taking the runoff from a rooftop, putting it in a large cistern, and they use that for car washes, like a green car wash. So instead of using potable water, they use that for reuse. The tank is used to wash the cars, and then there's a downstream rain garden that treats the runoff from that area. Green roofs are another a good option, probably a more expensive option of the different ones that I'm talking about. But it's a great way to take a otherwise impervious surface and try to retain stormwater runoff instead of it going downstream. And there's different types of green roof systems. Some are more complex than others, but the typical one shown on the top right here, where you have a growing media and vegetation on top of it. You have a drainage geocomposite layer, filter fabric, and then going down into your roof typical cross section with your roof deck and waterproofing membrane. The picture on the bottom left is actually from the Watershed Institute, so you don't have to go very far to look at it. Bottom right was where I went to school. It's on top of the library at Tufts University. So that's like a real simple one, right? It doesn't have to be all that complex. No photo credit for one that says Tufts. I took that picture. This is a project that we worked on. This is in Philadelphia, actually. This is at a treatment plant facility where they kind of want to walk the walk of doing this type of work. So it's at a wastewater treatment plant, but they wanted to go above and beyond for doing stormwater management from the site. CSOs are a big deal in Philadelphia. They ended up going with the green roof for the entire flat roof of this facility. This just shows some typical cross sections here of what was used for the green roof for that project. And you can see there's some gray areas through there. That's basically walkways. You can see it shown in one of the details here, but concrete pavers used between the green roof sections so that they could still get to access their HVAC equipment, for example, and different equipment they had on the rooftop. But this significantly reduces the amount of runoff volume that we have to manage downstream. Green roofs also have a place in urban areas where you don't have any other options, right? There's oftentimes in urban areas where there's no space to put in typical surface type green infrastructure BMP, so you either have to go underground or manage it on the rooftop. So you see this type of BMP used in those areas. Benefits of green roof reduces peak flow and runoff volume by retaining that rainfall that's occurring on the roof. It increases the time of concentration, which again goes to mimicking natural hydrology. It also has other types of benefits like mitigating the heat island effect, provides a layer of insulation on buildings, and adds community green space areas to urban areas. And it does have quite a big benefit. On the bottom right is how the green roof would improve the hydrology of a site from a hydrograph perspective, kind of shifting that time of concentration out in the storm, reducing volume and peak flows. I also wanted to talk about constructed wetlands. This really isn't a small green infrastructure approach, but of the ones that are larger, constructed wetlands provide one of the larger water quality benefits of the options that are out there. And we have used these quite a bit in the past. This is from a project also in Philadelphia, where they took a park and created a constructed wetland to manage stormwater runoff from the urban areas surrounding the park. And where the constructed wetland really shines is the treatment efficiency, right? So there's lots of processes that are occurring in a constructed wetland. It's a naturalized system where you can get really good benefits for TSS as well as nutrients. So this is just some photographs on the left shown there, and then a rendering of what the design looked like for the constructed wetland on the right side. And in New Jersey, there are design criteria for engineers designing constructed wetlands. There's 3 different zones that you can think about. There's deep pool areas where you have a good depth of 4 to 6 feet of water in those deep pool areas, and then you have different marsh areas that have different hydrologic zones. So you have a low marsh area where you typically have 6 to 18 inches in depth, and then a high marsh area where you have 6 inches of depth typically in that wetland area. And all of those different areas get planted with different types of species that are adaptable to those. Again, these are usually larger systems with larger contributory areas. You'd want to have at least 10 acres of contributory area to support the hydrology, is the rule of thumb. If you do have smaller drainage areas, you want to do a water budget to make sure that it can support that type of system. So maybe you have a small pocket wetland that's supported by groundwater or a base flow fed type system that will keep it wet. And that may be the case, but you want to do studies to make sure that it is going to have that hydrology to support the wetlands. You can also have a zone above the wetland that can provide additional water quantity benefits. So you can have extended detention where you hold back water like you would with a typical detention basin that occurs above the permanent pool elevation in the semi-wet zone. And these can be designed as online or offline systems. So they can be designed to treat all of the runoff from a certain watershed, or there could be a diversion structure. We've seen that a lot in the designs that we do, where maybe only the 1.25 inches the water quality storm gets diverted with a weir into this wetland, but then if you get a big flush of rain, it goes over the weir and just moves downstream, so you don't get that damage to the wetland that would occur from a big inflow of runoff. Manufactured treatment devices are also an option. These tend to be a little bit more maintenance heavy. They often require maintenance from vac trucks and that sort of thing. But there's different types of manufactured treatment devices out there that get different levels of treatment efficiencies. NJDEP and NJCAT have established which manufactured treatment devices are certified for different levels of treatment. So you can go on NJDEP's website, to the NJ Stormwater website, and get a listing of all the different types of manufactured treatment devices out there. There's a whole laundry list of them. Some of them are green infrastructure certified, and some of them are non-green infrastructure certified. So the top two are examples of green infrastructure MTDs. So there's the Filterra system by Contech, and the Hydro Stormscape by Hydro International, but these are more tree planters that use bioretention type media to treat stormwater runoff. On the bottom left is a hydrodynamic separator, and the bottom right is a storm filter, which has filter cartridges. So the bottom ones are non-green infrastructure. The top two are green infrastructure type manufactured treatment devices. All of them have 80% except for the hydrodynamic separator, which is 50%. That's typically what they're like. If it's a hydrodynamic separator type system, it would be a 50% treatment efficiency. Anything that's filtration or green infrastructure would be 80% typically. I wanted to talk about retrofitting detention basins. Fred talked about that earlier. I'll talk about that a little more because it is low-hanging fruit, and it's something that comes up a lot with municipalities because they have all these detention basins that they're trying to operate and maintain. Maybe they're sick of mowing it all the time because you got to be out there every week mowing it. And there's some benefits to reduced operation and maintenance costs and improved water quality. But it's things like getting rid of that concrete low flow channel, right? Replacing with a stone trench where water can sit and infiltrate, give it a chance to infiltrate. You might be putting in a forebay at the inlets to let sediment settle out before it gets into the larger system. You might create pockets of rain gardens within the detention basin where you do some replacement of soil to a more permeable soil to let water infiltrate, putting in different types of wetland plantings. Creating these curved edges instead of that straight concrete channel right through the bottom of the detention basin to increase the time of concentration, let water settle, infiltrate into the ground, soak into the ground. You're probably seeing a theme with all these different BMPs. It's different ways to do the same thing. This is from Stormwater. This is from stormwaterpa.org is the reference here. They have this graphic and have some guidance on doing this type of work. Another big component here is just the planting part of it, right? When you change out from a maintained lawn to a meadow type matrix of vegetation, you're going to really increase how much water you're soaking up, how much treatment efficiency you're getting, and improve the performance of the basin. And this is a project that we worked on that had a just typical extended detention basin with a concrete channel. And we retrofitted the stormwater management system here to include a rain garden, a vegetated swale, and then a detention basin retrofit where you can see on the top right there, we took out those concrete low flow channels. We put in stone. We let the kind of naturalize that detention basin to allow it to function to hold water more effectively. And this is just some photographs from that site showing the naturalized basin and reduced volume and treatment efficiency that you get from that type of system. I also want to talk about low impact development and sustainable streets. This kind of is going to, how do we use all of these different approaches of vegetated swales, of rain gardens, of tree planters, there's all these different tools that we can use in a sustainable street approach. And the benefits aren't just stormwater management, it's also the aesthetics, this idea of green streets with plantings, trees having a huge value, traffic calming, pedestrian accessibility in urban areas. There's all these benefits to using green infrastructure in our streets. And the other reason I bring this up from a standpoint of the MS4 permits is municipalities have street projects that come every year, right, that have grants to fund repaving roadways. Maybe those are opportunities where we can incorporate green infrastructure within those projects so that we can improve stormwater management, address these MS4 permits through other activities that the municipality is working on. And I also want to talk about some of the stream restoration work that we've done and pond restoration work. It doesn't have to be work that's up in the watershed. It could be within the stream itself. It's not always the easiest thing to do from a permitting perspective in New Jersey. I wish they would make it a little bit easier for this type of work. But this could have a lot of value, especially in areas of the site where you have very erodible soils, where a lot of that load that's going downstream is just erosion from the stream bank itself, from these systems that weren't designed to take that much water coming through. And these are some different projects we worked on. On the bottom left is a project in Monmouth County, where we did soil lifts to protect the stream bank. We did in-stream structures, rock veins, and different structures to try to protect the stream. This happened to be a project that was needed anyway because there was a pedestrian bridge that was getting eroded out. So we were trying to protect that bridge while also stabilizing the banks in the stream in that section of the river. I also want to mention on the bottom right here, this is at a lake. Doing plantings like this have a lot of value too. I'll talk about geese a little bit in just a minute, but this is one of the easiest ways to help protect against geese is blocking that line of sight, doing plantings along the perimeter of lakes, not having that maintained lawn go right into the lake edge. So projects like this can have a lot of benefits, from treating direct runoff into the lake, as well as that geese management issue. Great, thank you. Educational opportunities. This isn't really discussed that much, but we have to use this effort to try to take advantage of educational opportunities that come out of it. All the projects that we've worked on in watersheds have involved public participation and development of the watershed plans and involving the public in the project planning process, using those implementation projects as an opportunity to educate and outreach to communities, incorporating signage into the project so the public understands why these things are here, what benefit they have, which makes them want to take care of them. And just some photographs of different education programs that we've done with students in schools within these watersheds, which is, that's really what it's all about. So quickly, I'll run through some of the design, construction, and maintenance considerations for these facilities. On the design side, testing for infiltration facilities is really important. Chapter 12 of the the BMP manual, the New Jersey BMP manual, provides guidance on number of test pits and testing requirements. You want to go pretty deep with these test pits. It's 8 feet or twice the maximum water depth in the facility, 8 feet below the bottom. So it's a pretty substantial depth that's required on these test pits. You're looking at soil types, where you're seeing seasonal high water table, what the permeability of the subsoils are to know if you should design your system with an underdrain, for example. So that's a really important component of the design of these facilities. Also looking at groundwater mounding, we have to assess the impacts on the existing and proposed adjacent structures. So when you're trying to infiltrate a whole lot of water in one spot, we have to look at how that will impact the surrounding systems and how it will impact the performance of the BMP itself. In general, using a bunch of distributed BMPs instead of one centralized basin will have less of an impact. And there's guidance here in chapter 13 of the BMP manual. Clogging of infiltration systems. On the right there is we were doing an inspection. That's a basin that's not working as intended. And believe it or not, the whole reason for that issue there was they built the basin and they didn't stabilize the area that was running to it. There's a lot of clay in the area that was running to it. And so there was a layer of like 1 inch of clay on the top, and that was enough to just clog up the whole system. Water didn't go anywhere. That was actually an underdrain system. They couldn't even get to the underdrain, right? You'd dig through it and water would just go right down. So we want to be able to not put in that infiltration layer, like the bioretention media, for example, until we have that whole area stabilized. So typically we'll build these, we'll roughen the grading for these basins, for example, on a development site, and we'll leave maybe 2 feet to the final subgrade. We'll let that function as a sedimentation basin, and then we remove everything that's settled over time. We dig an extra 2 feet out until we get to clean soil. Components that are expected to receive trapped debris should be inspected and maintained. A lot of times it's just outlet structures that are clogged up, low flow orifices that are blocked up and cause standing water clogging of the system. Compaction during construction, this is another issue we often see. I put a little block on the truck so you wouldn't see the name of the company, but that's a pickup truck that's be good to just drive on the bottom of an infiltration basin before they put the soil down. But a lot of times, you know, folks from construction companies, maybe they haven't worked on this type of project before, don't know, you know, what they should be doing. They're just, that's a nice place to drive. So they drive down to the bottom. It's the quickest way to get to the outlet structure there. So, but we want to minimize construction vehicles driving over underlying soils. We want to use light earth moving equipment and prohibit any vehicles from driving over infiltration surfaces and bioretention media. Invasive species management. This is really about knowing what weeds look like is a big part of it. Another thing that we've found is that there's like the Ernst seed, for example, has some seed mixes that have 30 different varieties of native plants. And you end up with a system where you don't know what's a weed and what's supposed to be there. So sometimes it's better to make it a little more simple so that those that are maintaining can say, this is clearly supposed to be here, this is the type of vegetation, and these are weeds. Use plant identification sheets. We don't like using herbicide for obvious reasons, so using removal of invasive species by hand. Mulch is a really good tool, very simple, right? Just a good layer of mulch will help keep invasive species and weeds out. We talked a little bit about the Canada geese control. There are kind of the border collies that you can hire to come around, and they usually just chase it from one pond to the other pond, and then they go to that pond, and they go to just driving around the whole area. Really, that idea of an aquatic shelf, a meadow landscape around the perimeter to block that line of sight is a much better approach than just a maintained lawn like shown in the picture on the top right. But it's a really important aspect, especially with these larger ponds and wetlands, that we have more of a native landscape to help control that geese population. Mosquito control comes up a lot with the public, so wanted to mention that. Stormwater facilities can attract mosquitoes if standing water is present for more than 72 hours. That's where that comes from, that 72-hour requirement. But a lot of times it's this picture on the bottom right that's creating the mosquito problem. It's not your constructed wetland. It's these little pools of water. It's this concrete low flow channel that we'd rather have it infiltrating the water, where you have some buildup of leaves and then you just have 2 inches of water that's sitting there, right? So that's the type of things that we want to try to prevent. Trash and sediment removal. This is just something that needs to happen. And I like to look at it as, if you're removing trash and sediment, that's a good thing. That means it's not getting downstream. But it's inevitable. If you have a system that's collecting a lot of sediment, it's doing its job, you have to remove it at some point. And unfortunately, it's something that's a little more costly that you have to plan for. It would be more of a non-routine item if you have to go in and dredge, for example, but it might be something you have to do every 10 years to get in and remove that sediment. And this is just a listing of routine versus non-routine maintenance items. Routine things like removing trash and debris, mowing. Hopefully that would be more infrequent if we have more of a native landscape. Street sweeping, vacuuming of porous pavement would be a routine maintenance item that you have to go in there, back out that that'll open up the question.
Thank you, Brian. That was a lot of information. I know I'm going to have to go back to this presentation. Does anybody have a question?
Yes.
So both you and Fred mentioned that retrofitting detention basins was low-hanging fruit. So are there specific sizes of detention basins that make sense to be retrofitting, or is it just any?
Any. It's those detention basins that you go by that were put in the 90s that are perfectly mowed all the time, have a straight concrete low flow channel, where all those small storm events, it's just a channel of water going right through the middle of it, right to the pipe, right? And there's no benefit really to it. So you want to be able to modify those, that rest of the surface of the detention basin can work to infiltrate that water, not send it downstream, provide water quality benefits.
We've got one question from the chat.
Yes.
We see the need to reevaluate green infrastructure systems that rely on infiltration when sea level rise gradually raises groundwater level below those systems. And
there's going to be flooding very frequently in those areas. But it doesn't mean that you can't use green infrastructure in those areas. It's something that you have to plan for. And it's the kind of thing where you want things to work to provide some benefit now, even if in the future it's going to have some reduced efficiency. But I would say that you do want to be planning for, 50 years down the road, what's that groundwater level going to be like? It's pretty easy to calculate based on the projections and what sea level rise, especially in those coastal areas. It's almost, as that sea level rises, it's going to raise the groundwater by the same amount. So I think that's something that definitely needs to be considered, especially when we're designing for resiliency on coastal areas.
Thank you. Andrew, do you have a question?
A request, I guess, for you and anyone else who's trying to naturalize an existing basin or design a new bioretention system. When you're doing this, have the first 5, 8, 10 feet around all of your hard structures mowed and cleared so that your municipalities can come in and do their inspections without getting ticks and asking you to go clear this area so that they can actually see the structure, and berms as well, so that we can make sure that there's no tunneling.
Absolutely. And we've often put up like no mow signs on our systems because, with a picture, because then the landscapers know exactly where they should go up to, right? Because it could be the opposite problem where they mow the whole thing, right?
I like the picture idea. That's great.
Any other questions? Okay, Peter? Yeah.
Is there anything in the new rules that require, retention basins that were built 20 years ago that do exactly the same? Gather the water, send it out, to be upgraded, to be updated, everything. Clients who have these retention basins, and they very much like the look of something that has been retrofitted so it can be planted decently. Is there anything that requires them to do that?
No. The watershed improvement plans hopefully will trigger some of that work to be done. I will say there's a lot of grant opportunities out there for that sort of thing. A lot of the smaller grants are targeted at that sort of thing where you're just replanting and it's a small amount of money potentially that's needed to do the planting component of it. Like ANJEC grants, probably giving out grants for that sort of thing. But there's nothing requiring it in the regulations. If someone has an existing basin that was lawfully put in to change the vegetation or anything like that.
Last question.
Yeah, just quick, the pervious asphalt, have you found it, how long does it take to eventually was forced to fill in? Like how long is that?
Well, it depends on the site is a big part of it. It depends on how well stabilized the area is around it. And usually it's not like the whole thing goes at once. There'll be usually the part that's furthest downstream where all the sediment is collecting will go and get, needs to be backed out. No, you're going to want to be backing it out at least a couple of times a year is what would be recommended to have a back system go over it. So that's the number one thing why communities don't try to shy away from it. And it's the kind of thing where if, let's say you're a city, maybe you're just going to buy a back sweeper, right? So that you can do it. And then you're going all in on porous pavement. You've put in the funding to buy this piece of equipment so you can maintain all of the pervious pavement. It's more of an issue where you have like one system, right? And now you have to pay a contractor to come in to do it a couple of times a year. But that's definitely a maintenance item that has to be done in order to keep the system functioning.
Well, thanks very much to Brian. And thank you.